right, today we're going to work on lesson 3.1, which is on relations and functions. We're going to work on today is a definition of relation so we can identify what a relation is by using graphs or ordered pairs or tables or mappings. And we're also going to get into today what functions are and how to identify a function from a group of possible relations that could represent those. Okay, so first of all, let's start with definitions and terms here. A relation is simply the pairing of items. For us, it's usually numbers, right? But it doesn't have to be numbers. It could be variables and numbers, and you'll see different examples, but it's the pairing of items. And it can be written in a lot of different ways. Okay, one of the first things we work with is domain. All right, when we're given a relation, we're going to be asked to name the domain. So the domain is simply the first number in the relation pair. Generally, when we write relations, we think of them as ordered pairs. Okay, so it would be the x value in the ordered pair or the input value if we were looking at a function. Okay, the range of a relation is the output. It's the second number in the relation pair, or what we call the y, typically in an ordered pair. All right, now I mentioned that relations can be written in a lot of different ways. I'm going to show you a few of those now. Okay, the first thing they could do is what they call a mapping, which is they actually show you the domain in a group and the range in a group, and then they use arrows to connect. Okay, so in this mapping, 3, 5, we could write as an ordered pair that would represent that particular grouping. -4, -2 would be an ordered pair, 0, 2 would be an ordered pair, and that would represent that relation. Okay, we could do it as a table. X is the input, it's the domain, Y is the output. So 3, 5 would be a ordered pair. -4, -2 would be an ordered pair. 0, 2. Notice it's the same groupings there. We could do it as a graph. Remember that a graph is made up of points, and these points are ordered pairs. So this ordered pair is represented by -5, -2. This ordered pair is 0, 2. This ordered pair would be 3, 5. So those ordered pairs are the relation numbers we would look at. And then finally, they could give us an equation. So for an equation, we don't get specific ordered pairs given to us, but we could put in a number for x and find out what its output is. So if I put in 1 for x, y would equal 3. So 1, 3 would be an ordered pair. If I put in 2 for x, we'd get an answer of 4 for y. So 2, 4. So this equation doesn't give us the ordered pairs, but it gives us the ability to find ordered pairs that would fit it. Okay, a couple of question types now. The first thing we're going to work on is domain and range. So suppose this relation T is defined as follows. So here is the relation T. Relation means it's a collection of ordered pairs. So I have 4 ordered pairs given to me in this particular relation, and a relation can have as many ordered pairs as there are available to that one. The question is simply give the domain and range of T and write our answers in set builder notation, set notation. So the domain are the x's or the inputs. So 6, -2, 4, 0. That's my domain. So D equals the set of 6, -2, 4, 0. The range is the outputs. So 2, or the y's, I should say, 2, 6, 4, -7. So there's my range, 2, 6, 4, -7. Okay, pretty straightforward. The only thing you may see different tonight is sometimes they'll list these in ascending order. So they'll put the smallest first and then they'll work their way to the biggest. I just took them out as I saw them. Okay. Another question involving domain and range. Okay, we got to work off of this graph. So just to understand what the graph represents, it says the owners of a recreation area fill a small pond with water in 180 minutes. The pond already had some water at the beginning. The graph shows the amount of water in liters in the pond versus time in minutes. Find the domain and range of the function. Okay, it says write your answers as inequalities using x or y as appropriate. And we can click empty set or all reals. And this is part of the Alex question tonight, if it fits. So let's take a look at this graph for a second, though. Remember that this line is made up of all the ordered pairs that are on the line between these 2 points. So for example here, at time 0, there's 450 liters in the pond. So 0, 450 would be an ordered pair in the relation. Okay. And at 20, Minutes, you could see roughly, I don't know, we'd have to guess there, 575 or something. It's getting close to 600. It doesn't matter. We don't have to know exactly what these numbers are. We just have to understand what they represent. So it says name the domain and range. Okay, now remember, domain is the X values. So when I'm going to go look up to see where I'm on the line, and I'm going to use my X value. So this graph spans from 0 to 180 on the X. Okay, times 0, there's 450 liters in there. At 180 minutes, where they said the pond was full, there's 1,350 liters in there. So the X again is my domain. So the domain is all X's, all X's on this X axis such that it's greater than or equal to 0. So it's bigger than 0, and it's less than or equal to 180. So it's somewhere between 0 and 180. It could be 0, could be 180. So those are my input values. Those are possible inputs. Those are the domains. The range are the Y's. They're this axis. Okay. So as I look across here for my Y values, the smallest Y value I could have is 450. That's how much water starts in a pond at 0 minutes. And the most I get in the pond is 1,350. That's where the graph ends. So my domain are these numbers, and they span from 450 to 1350. So my Y's, which are my domains, have to be greater than or equal to 450. So I'm going at 450 up, but less than or equal to 1350, excuse me. So we're going down. So somewhere in here, all of my water values are. And then down here are my time values. So we have to just read it literally as X and Y's. Okay. Another example of this, just a kind of a different way to give you information. A construction crew is lengthening a road. Let L be the total length of the road in miles. Let D be the number of days the crew has worked. Suppose that L equals 4D plus 300 gives L as a function of D. The crew can work for at most 70 days. So they're capping the number of days they can work on this road at 70. Identify the correct description of the values in both the domain and range of the function, then choose the most appropriate values. Okay, so first of all, they ask us to name the domain. And the domain could be one of two things. It could be the length of the road, or it could be the number of days the crew has worked. So if you look at this equation up here, L equals 4D plus 300, we're going to substitute in the number of days, and that's going to tell us how many miles. So for instance, if day was 0, then 4 times 0 is 0, the length of the road is 300. If they work for 1 day, they're going to add 4 miles to the road. So 4 plus 300 is 304. So the days are our inputs. Okay. And the inputs are the domain. So the domain in this case is the number of days the crew has worked. Okay. Over here, it says choose a set of values that represents the actual domain. So they're going to give you a pop-up chart that looks like this. Okay. Now, what do we know about the number of days the crew can work? Well, they capped it at 70, right? And, we could start at 0 days. 4 times 0 is 0. So this road is 300 miles to start with. And then we're going to add 4 miles a day to it from here on out. So of these collections, the set from 0 to 70, the set from 4 to 300, the set from 300 to 580. This is the set of 0 to 300, the set of 70 to 580, the set of 70 to infinity. Which one of these fit? Well, we could work 0 days up to 70 days. Okay. So the set of all real numbers from 0 to 70 is my best choice. Okay. Based on the information. The range now are the length of the road in miles, because the range is the outputs or the Y values. So the outputs are the answers when I plug in the inputs. Okay. So what is the possible range here? Well, if they work 0 days, they're going to have 300 miles of road. That's how much the road starts at. And then every day we add 4, right? Now we can work a max of 70. So 4 times 70 is 280, plus 300 is 580. Okay. So this road is going to be from 300 to 580 miles long. Okay. See that? So our range here is from 300 to 580 miles. That fits this information. Okay. So you really got to look into it a little bit, but it's pretty clear. Remember that domain and range are inputs and outputs. Okay, the next idea here are functions. Okay, a function is a relation. Okay, in which the input and output, there is exactly one output for each input. So every input value is paired with one output. That's the easiest way to explain it. Let me go through some examples with you. Okay, this is a mapping. Does this mapping represent a function? Okay, well, is every input paired with only one output? And the answer here is yes. Now, I know you're going to see this and say, wait a minute, 2 and -2 are both paired with 3. Well, that's okay. They can be paired with the same number, but they can't be paired with two different numbers. Okay, let me show you. Now go over here and look at this example. There's a domain, there's its range. There's a domain, there's its range, right? This is a table. Okay, is this a function? It's a relation. Is it a function? The answer is no. The 2 was an input and it got an output of 3, and then they input 2 again and get an answer of -3. We can't have an input paired with two different outputs. Okay, this is okay. 6 and 5, 8 and 5. That's fine, but you can't have the same input listed. So you're looking for the same x value listed with two different y values. So that is a no-no. So that's not a function. Okay, here's a collection of ordered pairs. This is a relation. Is this a function? Well, again, what I do is I look for the x's. So 2, 4, 8, 4. Oops, I got an input of 4 twice. I had an input of 4 and it's paired with 7. An input of 4 is paired with 13. No good. Okay, no bueno. That's not going to be a function because my input of 4 is paired with two outputs. So this is really just a yes or no question. Okay, for this relation, decide whether or not it's a function. Okay. So again, remember I said it doesn't, it can be, a relation can be just items paired. It doesn't have to be numbers. So for example, rock is paired with 8 and then rock is paired with 2. Pen is paired with -1, paper with -9, and paper with 1. Is this a function? Well, no, because you have an input of rock and an output of 8, an input of rock and an output of 2. You can't have the same input paired with two outputs. Paper does the same thing. Okay, so that's not a function. Move over here. Is this relation a function? Well, one's paired with 2, and then one with 8, and then one with -9, and then one with 1. If you wrote out these ordered pairs, you'd see the input of 1 4 times paired with 4 different outputs. That's no good. Not a relation or not a function. Is this relation a function? Well, again, what I look for right now is the inputs V, N, S, T. Did I ever have the same one listed twice? No. So this is a function. Same thing here. -7, 8, 8, -8. Whoops. I got 8 as an input twice. One time it's paired with J, one time it's paired with T. Can't have an input with two different outputs, not a function. Okay, so that's your checklist to go through. Okay, another way to test to see if a relation is a function is what we call the vertical line test. Okay, this is terms whether the graph of a relation represents a function. The way it works is if you can draw a vertical line and you can intersect the graph at two different points, then it's not a function. What that would mean is you had two inputs with, or two of the same inputs with two different outputs, and you can't have that. So let's look at a few examples here. Okay, this first one is a graph of just specific ordered pairs. So this is just kind of a list of ordered pairs if you thought about it it being written out. So can I draw a vertical line here and hit any of the 2 points at the same time? Well, here's a vertical line going through the first point. It doesn't hit any other points. Here's a vertical line going through the next one. Doesn't hit any other. Only hits that one point. That vertical line only hits that point. That vertical line only hits that point. That vertical line only hits that point. So is this relation a function? Yeah. Every input has its own output. Now this is a shape, but you remember that the shape is made up of ordered pairs. So there's a collection of ordered pairs that create this line, a set of ordered pairs that make this one in here. So can I draw a vertical line and hit this shape in two different spots? The answer is yes. And because I hit it here and hit it here, this is not a function. That means I got an input value that has two different outputs. Now, this is what we call a step function. All right. So to understand this segment ends right here. It goes there's a collection of ordered pairs all the way to this point, and then it ends here, and there's no point here. Notice that this is darkened in. So if I draw a vertical line here, since this is an open circle and that's a closed circle, then we're not hitting a point here, but I am hitting a point there. Same thing here. I'm hitting this point, but there's no point here. They're showing this because, yes, this is a function. I don't have two inputs or an input with two different outputs. Okay, graph 4, is this a function? Well, right away, right here, draw this vertical line and hit it in these 3 points. That's all I need to say no. Is this going to be a function? Draw this vertical line, hit it at 2 points, and you can draw any vertical line you want. You're going to hit it in 2 points. And the question is, can you do it? Not can you not do it? Okay, so that's not a function either. Okay, the last thing we're going to do is look at graphs and try to fit a narrative to it. Okay, just so we understand the whole input output, the relation, how the two variables are related to each other. So for the scenario below, choose the best graph. So this just says at the end of the race, the runner slows down. So we got to look at what our graph is made up of. The y-axis, okay, which are our outputs, are the runner's speed. The x-axis, which are our inputs, is time. So at time 0, the runner's not going fast at all, if he's even moving. As time moves on, speed increases. So in this one, as time goes on, the runner's getting faster. That's not what they asked for. In this one, as time progresses, the runner's speed decreases. That's what they're looking for, right? At this one, the runner starts at a speed and stays at a speed the whole time. That's not this. In this one, I don't know what it even means. Okay. So you start here at some point in time, and then the runner speed just goes off the charts. All right. So what they're looking for is this one. Okay. As time goes on, the runner speed decreases. So we got to really relate these two together. So Austin walks home from school. So again, our X, which would be our inputs, is time. So as time increases, they're saying the Y represents the distance from home. So in this example, as time increases, he's getting farther from home. In this example, as time increases, his distance from home is decreasing. This one, as time increases, he's staying the same distance away from home. And this one just says at one point in time, he's a crazy distance away from home. I don't even know what that means. Okay, so this is the one. As time increases, his distance from home is getting less and less and less. Okay, a little bit more complicated couple of these. Maria's delivering a pizza to Mark's house. She drives at a constant speed toward the house until she hits a traffic jam. Then she's got to stop for several minutes. After she starts up again, she begins to drive at a faster speed than before. Okay, so now you got to understand this. What this represents is the distance to Mark's house. Okay, so she should be heading down. So she gets to his house. Okay, this is over time. Okay, so I don't know what this one shows, that she's a constant distance from his house. So she's not getting any closer to it. She gets closer to her house, then she gets farther away. And then she's that same distance she started away. So that's not it. This one shows she's getting closer to his house at a constant speed. Now she's not getting towards his house. She's in a traffic jam, so she's not getting any closer to the house. And then at the end of the traffic jam, she starts getting closer to the house faster. That describes our scenario. Let's talk about these though. This one says she stays a constant distance away from the house. Then she gets really, really quickly gets far away from the house, and then even farther away yet. So that's not it. This one's kind of the same as the last one. Okay, so the only one that fits our scenario is this choice. Okay, this last one, Keisha's driving on the freeway at a constant speed. She then speeds up to pass a truck, and after she passes a truck, she exits the freeway and slows down. So X is time, this is speed. Okay, so if we kind of think our way through this, so as time progresses, she's driving fast, right? So she's driving faster, hits this traffic jam, and now her speed is, or no, I'm sorry, now she speeds up to pass a truck, right? But in this case, her speed stays consistent, and then it goes down really fast. Okay, if you look at this one, okay, so she's going at a constant speed, which is what they said to start with, right? Her speed is constant over time, and then it increases and then she levels off again. That's not what it says, right? This one, she's going at a constant speed, speeds up to pass the truck. Once she's past the truck, she slows down. This one would say her speed increased. She went at a constant speed, then her speed decreased. So the only choice is this one. But you got to really talk your way through it, you know? Okay, so that's relations and functions. I'm going to give you guys an assignment that you need to work on Alex. Okay, it's a lot of the same questions I just showed you, very similar to the ones you're going to see on Alex. Okay, so hopefully you took some notes, wrote some things down, and use that information to help you on the homework tonight. All right, I'll let you get at it.